This PowerPoint is over waves. A definition of wave, it's a disturbance in a given medium that carries energy from one place to another. It's very important to realize that it's not the matter that actually moves through a wave, it's the energy that moves through a wave. The matter itself is vibrating back and forth, whether it's vibrating in the same direction as the energy is motion or perpendicular to the energy's motion. The matter is basically staying in the same location as it's vibrating back and forth, but the energy is moving from one place to another. A pulse wave is a single disturbance in a medium, and a continuous wave is a set of disturbances that are occurring over and over in a pattern that usually you can get some sort of a period or a frequency out of. Types of waves, we got longitudinal waves. These are the types of waves that the medium vibrates in the same direction as the movement of the energy. And then the wave consists of series of compressions and rarefactions, and the example we have for this is going to be sound. Basically what happens is as the compression moves forward, it leaves a gap behind it that's a rarefaction. So the compression is the more compressed part of the wave, or the higher pressure part of the wave, and then the rarefaction is the spread out portion of the wave, or the lower pressure of the wave. So if we have this wave that moves forward, you can see that we have a compression that moves forward and then the rarefaction that's spread out that's behind it. This is an example of just we have areas here that we have high compression, and then low compression, which is our rarefaction here. So high pressure to low pressure, high pressure to low pressure. The distance from one high pressure to the next high pressure, which is compression to compression, that's going to be the length of the wave. We can also measure the length of the wave from a rarefaction to a rarefaction, because that's going to be the same distance. The second type of wave is a transverse wave. This type of wave is where the medium vibrates perpendicular to the movement of the energy. So it vibrates up and down as the energy moves forward. This consists of a series of crests and troughs, and then light is going to be the example we have here. Light is actually a double transverse wave because it vibrates in both the electric field and magnetic field. We're not going to get too deep into that in this PowerPoint, but it is a transverse wave. So we have motion of the matter up and down, and as the motion of the matter goes up and down, it vibrates and moves the energy forward. So we have our example here. We got the which kind of looks like a wave from like a surface of water or something like that, and that's actually a different type of wave. But this we have crests and troughs and crests and troughs, and then the distance from one crest to the next is going to be our wavelength again. The amplitude is the maximum displacement of the wave from the equilibrium position or the rest position. So if there was no wave disturbance in this medium, it would be a solid sheet, but since there is a disturbance, it has these ups and downs, and these ups and downs, the maximum displacement is referred to as an amplitude. The last type of wave is a surface wave, and this wave is where the medium vibrates in both the horizontal and vertical direction, so it has actually a circular motion, the combination of up and down and side to side. And water waves tend to be a surface wave, although when we look at water waves, sometimes we just look at the up and down motion of the wave, and so we kind of call it a transverse wave, but it's actually a surface wave, because if you've ever been in the ocean or a lake, when a wave passes by, you get pulled into the wave, then lifted up, and then you get pushed forward and then back down, and that's your complete circular motion. And then the circular motion is what causes that wave to move forward as each of these parts, the medium, moves in its circular pattern. So we see that here we have a point that is going to be rotating circularly, and that point is rotating as the wave moves by. As this comes by, let's say you're right here. As this wave starts moving forward, you're going to get pulled up into the wave, and then you get pushed forward and then back around and moved in this circular pattern. All right, some properties of waves. First of all, the wavelength. We kind of discussed that already. It's the distance between two like points on the wave, which could be a compression or crest to crest or something of that nature. So you have a wavelength between these two these two crests and these two troughs. That give you the wavelength. But if you look at this, you may think that's a wavelength because they're two like points, but in fact they're not, because you have the wave coming down at the rest position here and it's coming up at the rest position here. So if you want to say two like points, you would say from here to here, and that would be a full wave, so that would be one wavelength. It's a lot easier to go crest to crest or trough to trough because those are easy points to pick out on the wave. Next wave property is period and frequency. Period is the amount of time it takes for one wave to pass by. So if you think about, you got a continuous wave, so you got these waves that are passing by. The amount of time it takes for one wave to move on to the next wave, so that, you got one crest that passes by, and the amount of time it takes the next crest to pass by, that's the period. Frequency is the number of waves that pass in a given second. So if you're measuring the amount of time it takes, let's say you measure 10 seconds and you count 5 waves that pass by, then that means you're going to have 5 divided by 10, which gives you 0.5 waves per second. For the period, if you have 10 seconds and then 5 waves pass by, then that means it's going to be 2 seconds per wave. So you can kind of see the relationship between period and frequency. And the next slide is going to be, we're going to do an example of that. So here we have our crests and troughs. We got our wave that is passing by. So we got time is going to click down as this line right here measures the number of waves that pass by. And we get a total of 15 wavelengths that pass in 5 seconds. So what's the period and what's the frequency? First of all, the period is going to be the amount of time that it takes divided by the number of waves. So 5 seconds divided by 15, that gives us 0.33 seconds. So one wave passed by in 0.33 seconds. To find the frequency, we take the number of waves and we divide it by the amount of time. So we take 15 divided by 5, and that gives us 3 waves per second, or 3 1/over seconds, which is a unit of hertz. So you can see that 0.33 seconds per wave and 3.0 waves per second. So we've got 3 waves per second, or 0.33 seconds per wave, and you can see that those are actually going to be inverses of each other, and that's going to be the relationship between period and frequency. All right, so this relationship, they're inverses of each other. So if I take the period and take 1 over the period, that's going to give me the frequency. Or if I take the frequency, take 1 over the frequency, that's going to give me the period also. And then the unit we're going to have for frequency is called hertz. The next wave property we're going to talk about is the speed of the wave. Now, we've talked about the distance between each wave crest or each compression in a wave, and that's the wavelength. And we talked about the amount of time it takes for one wave to pass by, and that's the period. So if we take the wavelength and divide by the period, then that's going to give us the speed of the wave. Now, oftentimes when we talk about the speed of the wave, we don't talk about the period, we talk about frequency. And we know that frequency is going to be 1 over the period, so if we're dividing by period, it's the same as multiplying by frequency. So the wavelength times the frequency is going to give you the speed of the wave, which is v. Now, something to note in college, this Greek letter nu is sometimes used for frequency instead of this f, and that's just for your own knowledge. Now, something to keep in mind about the speed of a wave. The speed of the wave does not change as long as the medium doesn't change. So the medium itself is what has to change in order to change the speed of the wave. That means if we have a frequency of a wave, and let's say we have another wave that has a higher frequency, well, it's not going to get from one place to another any faster because its frequency is different. The same with its wavelength. Changing the wavelength doesn't change the speed of the wave. It's still going to take a certain amount of time to get from one place to another, regardless of its wavelength. And the biggest misunderstanding is the amplitude, which we haven't really talked about too much, but its maximum displacement from the rest position. The amplitude is oftentimes thought of changing the speed of the wave, when in fact it doesn't. If you think of somebody who's shouting, the amplitude is how loud they talk. And if they shout really loud, you may think that it takes a shorter amount of time in order for that wave to get to the other person's ears. In fact, it doesn't. The amplitude has no regard as far as how fast the wave is going. So for sound, the temperature and pressure are going to be the things that change the speed of sound. So how loud you speak is not going to determine how fast the wave is going to move. It's going to be the temperature, the pressure, and it's actually going to be the makeup of the air itself. Now, for an electromagnetic wave, the electromagnetic fields cannot be changed. So the speed of light is actually going to be constant, regardless of how you look at it. So let's look at this example right here. We assume the medium doesn't change. What will happen to the wavelength of a wave if you increase the frequency? Now here's the equation. The speed's going to be equal to wavelength times frequency. So if we increase the frequency and this side of the equation is going to be the same, that means the wavelength has to decrease. Now let's think about that logically. Frequency means the number of waves that are passing in a given amount of time, in 1 second. So if there are more waves passing in 1 second but the speed of the wave doesn't change, then that means there has to be a shorter distance between those waves. And that kind of goes along with the fact that if the frequency increases, then the wavelength has to decrease. So the next question is, what will happen to the frequency of the wave if you shorten the wavelength, if you get a smaller wavelength? Well, that's decreasing the wavelength, which means the frequency is going to have to increase as a result. All right, so in this example we have in music, a B note has a frequency of 247 hertz and the wavelength is 1.34 meters. What's the speed of sound, or the speed of these waves in air, which is called the speed of sound? Well, we take our wavelength times frequency. It's going to be 1.34 times 247. That's going to give us our speed of sound, which is 331 meters times hertz. And since hertz is actually 1 over seconds, then that's going to be meters times 1 over seconds, which gives me meters per second, 331 meters per second. The next example, suppose we have a planet emitting red light. Red light is known to have a wavelength of 7.00 times 10 to the negative 7th meters. Knowing the speed of light, what is the frequency of the light? Now the speed of light is going to be 3.00 times 10 to the 8th meters per second. So if we take the equation, the frequency is going to be equal to the speed divided by wavelength. That's just the rearrangement of the equation that we used before. And if you rearrange that equation, we're going to divide by wavelength, so that's 3.00 times 10 to the 8th meters per second divided by the wavelength, which is 7.00 times 10 to the negative 7th. And we get that the frequency is going to be 4.29 times 10 to the 14th hertz. So that's 4.29 times 10 to the 14th hertz. That's 429 trillion times per second. That's a lot. All right, the next example, let's say we have that 429 trillion times per second, 4.29 times 10 to the 14th hertz. What's the period of red light? Well, if you remember, the period is going to be 1 over the frequency. So we take 1 over 4.29 times 10 to the 14th hertz, and that's going to give us 2.33 times 10 to the negative 15 seconds. Very small amount of time per wave. All right, a couple wave behaviors we're going to talk about is the superpositioning of waves. When waves interact with each other, they actually pass through each other as if they're not even there. With objects, with tennis balls, for example, when two tennis balls meet, they bounce off of each other. But waves don't do that. They pass through each other. So what happens if you have two waves that are on the same side as the rest position? So we have a crest here and a crest here that are both moving toward each other. And this is the same as a trough. If you look at this upside down, basically you got a trough and a trough that would be moving toward each other. So what's going to happen here? As the two waves meet, they actually add to each other, which is called constructive interference. And as they pass through each other, you can see that the wave, this one moving to the left, is going to pass right on through and just keep moving to the left. This one moving to the right is going to just keep on passing on and moving to the right. And when they're meeting at that moment in time, they're going to add to each other, but when they separate, they move on as if they didn't even interact with each other. The next part is, let's suppose they're on opposite sides of each other. We got a crest and a trough, and this is not just transverse waves, longitudinal waves. Let's say you get a compression and a rarefaction that meet. Well, what's going to happen is destructive interference. Since they're on opposite sides, they're actually going to take away, they're going to subtract from each other for just that moment in time until they pass completely through each other, and they're going to move on as they were before, as if they didn't even meet. So here's an example. We've got two crests that are meeting, and as they meet, they go through each other, and then they add for just that instant in time, but then they continue on as if they didn't even interact with each other. Here we have two waves that are, they have the same wavelength, but they have different speeds. Now, I can't think of an example of where this can actually happen because all waves moving through a medium are going to have the same speed. But it's kind of interesting to look at this as one is moving faster than the other, then you have constructive and destructive interference. So right now we have constructive, and then you got the crest and the trough meet, that's going to be destructive interference. Now this is an interesting phenomenon. If we have two waves that have the same speed, but one has a slightly different frequency than the other, we can see here that we got a crest and a crest that are lined up with each other, but then a little bit later we have a crest and a trough that are lined up with each other. Well, that's going to give us this phenomenon, which is called beats. And basically this increase and decrease of the amplitude is what's going to cause a beat, and it's kind of a wah sound that you hear when you hear two sounds that are slightly out of tune. They're going to have just a slightly different frequency from each other, and you're going to hear a beat frequency in the process. All right, standing waves is a continuous wave that has points of no movement, which is called a node, and a point of maximum movement, which is called an antinode. So basically what you see, for example, with a slinky, you're going to see a vibration of the slinky. You're going to see one part moving up and down a lot, and then one part that's not moving up and down at all. This is going to be a combination of reflections and interference. So basically what happens is we're sending a wave down this way, and when it reflects, it comes back this way and interferes with itself. So as it passes through, we get this standing wave where we get crest that becomes a trough, and then a crest becomes a trough, back and forth, back and forth. Now if you notice, we get a point right here where we have no movement up or down. That's called a node. And then the points right here where we have maximum movement, that's called an antinode as it vibrates back and forth. Now if we notice a full wavelength, we start with a node here, and then we get a trough, and then we get another node, and then we get a crest, and then we get another node. So the entire wavelength is going to start from node and go to another node and a second node. So it's going to be two of these antinodes in between. So it starts from one node, goes to the next, and then the next. So that's going to be our full wavelength. Is going to include two of these that are vibrating up and down to give a full wavelength. All right, so a couple of examples we do in class. We do a demonstration with a spring that we measure the wavelength and find the speed of the wave for those different wavelengths for a standing wave.